Hey y'all, in this video, I would like to go over an example where using local coordinate systems are actually useful and make it easier to solve the problem. So here's an example where we have a block. It's just sitting on this incline and it's going to start from rest, slide down the incline, and then fall off this table that this wedge is on, and then fall all the way to the ground. Our problem that we want to solve is how long does it take our box to go from the top of the wedge all the way down to the ground. Now, some things that you can realize right away is that this is a kinematics problem, but it's a kinematics problem that has two parts to it. Your block will have one acceleration going down the incline, and then once it leaves the incline, it will be in free fall and have another constant acceleration for the rest of the problem. So this already splits into two parts pretty nicely. Let's use two different coordinate systems for those parts. Why? Because if I want, I could create a coordinate system that's slanted like this, right? Have the origin be where the object starts. We know that slanted coordinate systems are great when you have inclines, but if I just use one coordinate system, well, imagine I have slanted axes over here and trying to figure out the motion of the object on this part of the problem. Very confusing, not very clear. Likewise, suppose I have one global coordinate system where I have straight up and down axes. That's great for this part of the problem, but over here it's very unclear what to do with this mass right there. So we are going to use two different local coordinate systems. We're going to have a slanted coordinate system, which I'll write in red. The origin starts where our object starts moving at the top of our ramp. And then we'll have another coordinate system that will keep track of the motion of our object once it leaves the ramp and goes into free fall. Notice that I've largely kept the directions the same. I've kind of kept the upwards sort of direction positive and the rightwards sort of direction positive because that makes it easier to stitch our two coordinate systems together, as I've discussed previously. But all right, so this is what we're going to do. So now we have a kinematics problem here, so we've got to list out our tower of equations. Now notice our mass for the first part of the equation, because of the tilted coordinate system, it's only moving in the x direction. So we only have one-dimensional kinematics for the first part of the problem. So let's go ahead and list out what we have then. So in the x direction, which is all we have, there's no movement in the y direction in the red coordinate system for the first part of the problem. We have our initial position. Well, we put the origin there, so that's 0. There's our final position. What's that? Well, let's think about our block again, or our wedge. We have a theta here. We have an h there. But since our coordinate system goes like this, since it's tilted, you'll see then that the hypotenuse of this right triangle right here, which I'll call D, that is in fact our x position, because our x-axis goes along the surface of our incline. So if we solve for D, we'll be able to get x final at the bottom of the ramp. You can use trigonometry to do that. We have that sine of theta is opposite over hypotenuse, and therefore the hypotenuse is h over sine theta. All right, and we could keep it symbolic, but I'll put in some numbers for you. We know that h is 1. We know that theta is 30 degrees. And so this is 1 over 1/2 is equal to 2. All right, so x final then is going to be 2 meters. It's positive 2 meters because I made the positive direction down the ramp, right? All right, then we have initial velocity in the x direction is 0 because it starts from rest. Then we have final velocity in the x direction, and that's going to be an unknown. Acceleration in the x direction, as you know, for slanted coordinate systems, for inclines like this, the gravitational acceleration has to be broken into components. And so you'll get g sine theta or g sine 30. For our acceleration, notice it's a positive acceleration because once again, we made the down the ramp the positive direction. And then finally, we have time, which is the thing that we want to find. All right, so if we want, we could then use kinematics to find either final velocity or time. You could use your v squared formula, v final squared equals v initial squared plus 2a delta x, to solve for final velocity at the bottom of your ramp there. And you could use another kinematics equation to get time. So we want time, so let's go figure out what that is first. In fact, I'm going to label this. This will be t1. So that'll be the first part of our motion. And then the second part of our motion, the time it takes to go from the bottom of the ramp to the ground, will be t2. All right, well, let's solve for it then. So what do we have? We have time, initial velocity, acceleration, and position. So that suggests to me our 1/2 at squared formula will be useful. So x final, x initial is 0, v initial is 0, and so we just have 1/2 a. So that's g sine 30, and then t squared. All right, so then we can use this to solve for time. Let's just move this around a little bit first, though. So we get 1/2 g times 1/2, and then that's t squared. And then so we get g over 4 t squared. So then I can move that to the other side and take the square root to get that t is equal to 8 over g, which if I put that in a calculator is about 0.90 seconds. So we have t1. And that's going to be root 8 over g, just keeping it exact. But we're not done yet, because to stitch these two equations together, it's going to turn out that we will need our initial velocity in the blue direction. That should make sense, right? Just intuitively, right? Because if you're trying to figure out projectile motion in the blue coordinate system, you're trying to figure out, well, I want to know what's going on to my mass as it goes down to the ground. And to do that, my mass is in free fall motion, it's in projectile motion. I'm going to need to know its initial velocity here. Well, if I need its initial velocity here, then I'm going to need to know the final velocity in the red coordinate system, because the final velocity in the red coordinate system will then turn into the initial velocity in the blue coordinate system. So let's go find our final velocity then. We can do that using our v squared formula, as I mentioned before. So let's do that. We get v final squared equals v initial squared, which is 0, and then 2a delta x. So x final is 2, x initial is 0, so 2 minus 0 is 2. And so moving this around a bit, or rather substituting in for some of the values, sine 30 is 1/2. And then we have a 2 there, cancel, cancel. So you get 2g, and therefore v final in the x direction is square root of 2g, which you could calculate if you want and get a number out of that. But I'll leave it as root 2g. All right, so that's the red coordinate system. Now let's talk about the blue coordinate system. To talk about the blue coordinate system, we're going to need to think about the velocities so we can stitch our two coordinate systems together. But firstly, notice we have 2D projectile motion once the mass leaves the table. So we're going to need to create an X and a Y tower of information. So in our blue coordinate system, X initial is 0 and Y initial is 0 because our origin is right there, where we first start keeping track of the motion of our object, where our object first leaves the table. So 0, 0. X final is unknown, but it'll be this distance, right? Which we typically call the range. So I'll just call it R, though it's an unknown. Our Y final, we do know that. We go down h meters from here to here. But since the up direction is positive in the blue coordinate system, that means our y coordinate at the ground is minus h, or which we have as minus 2 meters. All right, then we have our v initial in the x direction and our v initial in the y direction. So here, let's go think about the situation a little more carefully. Let's create our wedge again. right? And then let's extend this line out like this, extend this line out like that. We know that this is theta, and we know that this is theta. We know our object, as it's leaving the ramp, is going to have a velocity that looks like this. Oh, well, look at that. We can then break this velocity according to our blue coordinate system, according to x and y axes of our blue coordinate system, using the same angle. So this velocity here becomes the initial velocity in the blue coordinate system, and we can break it down into x and y components. All right. So here's our initial velocity. Then this is our initial velocity in the x and our initial velocity in the y. We can use sine theta to get the y and cosine theta to get the x. So we have v initial cosine theta, and then in the y direction, notice that because up is positive, but this vector is going down, it's going to be minus v initial sine theta. All right, but what is v initial? Well, v initial is the magnitude of this vector. The magnitude of this vector is just the v final in our red coordinate system. So as we've discussed on other occasions, the final value in one coordinate system becomes the initial value in the other. So v initial is root 2 g. So I can write this out a little bit more as root 2 g cosine theta and minus root 2 g sine theta. All right, and then the final velocities, they're unknown, but we probably don't care about them because we're really just interested in time at this point, and there isn't another part of the motion, so we don't need to worry about finding in final variables as inputs to the next part of the problem. Right, acceleration in the x direction is 0, as it always is for these problems, and then minus g. And then finally, we have time, which is going to be the same for both the x and the y, as time is always the same in both directions. It binds the dimensions together. All right, well, looking at this, we want to find t2. So we want to figure out how long it takes to hit the ground. Looking at this, you can see we have more information in the y direction. We don't know what big R is, but we know what all these other quantities are. So let's look at the y direction. Alternatively, you know that when you're finding for how long it takes an object to hit the ground, usually the y direction is a good bet. So we want time, we have acceleration, initial velocity, and positions. So the 1/2 at squared formula sounds good to me. So we have y final equals y initial of 0. Then we have v initial in the y direction. And then we have acceleration in the y direction. Can't forget my time. And there we go. Unfortunately, this is not an easy thing to solve. You'll have to use the quadratic formula for it. Just add the 2 to the other side, and you'll see that you get a nice quadratic equation that can only be solved by the quadratic formula. Factoring will not work. Or you can use Polysolve or some other computer program to solve for it. But you do that, and you'll find out what T2 is, and that'll be your answer for here. And then the total time, which is what we actually wanted to find, is just going to be T1 plus T2. All right, so that's that problem. Notice how it became a lot easier using 2 local coordinate systems and tying them together instead of using 1 global coordinate system. I challenge you to try to either use 1 global coordinate system with straight up and down axes or 1 global coordinate system with slanted axes and see how it turns out. You should get the same answer, but I'm sure you will find it to be much more difficult.